Is that better? Are we live? Yeah, sorry about that. So, just getting things started here. So, for today, the plan is to talk about applications of linear functions. So we talked in our stream last week about what linear functions were and what functions were in general. And this week we want to dig a little bit deeper into where linear relationships arise from the world around us, and how do we understand how to discover and then use a linear function model to make predictions about real world situations and phenomena. So there's kind of a couple of goals for today. Applying linear functions. The first goal is that I just want to go back to sort of what we talked about last week and review slope and intercept, not just from the mechanical perspective of y equals mx plus b, and sort of discovering an equation for a set of linear data, but I want to focus for us today on interpretation. So not what is the slope, what is the intercept, but really the question, what do these things mean? What do they tell us about a real situation that we might have some data about, that we might care to make a prediction about, and so forth. So, for example, if you're working at a nonprofit organization or something, and you're making a sales or a forecast of memberships, and you get a slope and you get an intercept out of this process that we're going to talk about today, and then you have to go present that to your executive board. How are you going to describe to those people, what does the slope actually mean? What does it tell us? Why should we care about this number? Because ultimately, at the end of the day, that's what all of this mathematical thought and practice is supposed to be about. It's supposed to be about conveying an idea, conveying information in as precise a fashion as possible, so that people understand it. Not just other math students, not just your math professors, but people out there that you interact with on the job and in your life day to day. So if we're going to do that process of communication, how do we do that? How do we interpret the meaning of a slope and an intercept? So that's kind of goal number one. I want to reach back into what we might call kind of the sterile examples that we talked about last week to get some motivation for that. But second is I want to tackle that real world data question. And what I mean by that is that if we go out into a practical situation and collect some data, and then we want to use what we're learning about in this chapter to discover something about that data, the first question that we have to answer is how to turn data into a formula. Because we could be the most skilled, fluent practitioners of algebra in the world. We could be algebra whizzes on the math team in high school, all that wonderful stuff. But if we don't have a way of getting a formula from the world around us in some way, then none of that symbol pushing is going to matter in a very real sense, right? That unless the equations that we manipulate have meaning behind them, then the manipulations that we do to them, solving them, simplifying them, all that wonderful stuff, those things don't really have a whole lot of practical meaning outside of our ability to reason analytically and to persist in solving problems and all those wonderful high-minded things. If we want to be able to truly, concretely connect these skills with things in the real world, then we need to cross this bridge. How do I discover a formula out of a set of data? And this is made complicated by the fact that anytime we collect data from the world around us, there's a process of measurement that's involved. And anytime there's a process of measurement, there will always be a certain amount of error involved in that measurement, where even if something in the world around us is governed by an exact linear equation of the kind that we studied last week, the process of us taking measurements is going to introduce a little bit of variability and fluctuation in the observations that we take. One of the big themes in the third act of our course, the final act of our course this semester, is going to be thinking about uncertainty and how do we quantify uncertainty and probabilistic events. We'll talk about probability, we'll talk about statistics. And the process that we're going to talk about today, it's called regression, is truly a statistical process. It's a process by which we take a set of data that's collected, say, from the world around us that could be pretty noisy. But if there's an underlying linear relationship that relates the quantities that we've measured, then we should be able to draw to a relatively high degree of accuracy. In other words, a relatively low amount of total error. We should be able to draw a straight line through those data points and then measure the slope and the y-intercept of that line that we draw. And then from that slope and that intercept, we should be able to extract some meaning. So we want to be able to do this interpretive process with the real-world formulas that we got out of the data we collected from the world around us. So that's the ultimate goal for today, is to look at those two things. How do we turn data into a formula? And for us today, this is going to be a process that we infuse with technology. After all, anytime we're working with data of a sufficient size, if we have a bunch of data points, and really the best predictions are typically made on the basis of the most data. And so some of the data sets that you might work with in this process could have hundreds or even thousands of different data points that are a part of your data set. And so anytime things are at that scale, we're not going to be wanting to do a whole lot with a pencil and paper on this. So particularly today, I want to talk about how to use Excel, spreadsheet software, to do this process. This is in your online homework system, the technology of choice. I think it's also for most of you going out into the world, into the workforce and so on after you graduate, this is going to be the technology tool of choice out there in the world too. So there's a lot of practical value and currency, not just to learning how to do this using Microsoft Excel, but also learning how to do really anything using Microsoft Excel, because that is a piece of software that powers a ton of businesses, nonprofits, governmental entities and so forth out there. So chances are, whatever your major, if you're watching this today, after you graduate, there will be an occasion for you to use Excel at some point in the workforce. So great to know. We'll get some exposure to it today. So let's start by just going back and setting the table one more time with what we talked about last week. So linear functions. So actually, I'm going to take a moment and pull up the slides from the last streaming session that we had. We'll use this as our sort of a recall of what we did before. So last week we explored this relationship using data that I just made up, just to illustrate the mathematical point. But it was a relationship between the number of employees that are in my company, maybe that's grown over time or something, and the amount of money that I've had to pay as an employer in health insurance premiums, right, to cost share them with my employees. And as the number of employees went up, so too did the amount of money I had to pay in premiums also go up. But it did so in a way that was very predictable, right? That what we discovered was that every additional employee that I added to my workforce, if I were to add one more employee, what would happen is that the amount I would have to pay in premiums would go up by $3,000. And that was a consistent relationship between all 5 of the data points that we had in our data table. Every time I added one more employee, I added $3,000 more in premiums. So when I added 7 more employees, I added 3 times 7, $21,000 more in premiums, and so forth. And in our graphical picture, that showed up as the data points all lying on a straight line in the rectangular coordinate system, the XY coordinate system. And the quantity that we associate to that line that conveys that information about 3 to 1 was this quantity that we called the slope of the line. So just as a reminder, what the slope was telling me was it was letting me observe that, for example, between these two data points, there was $21,000 more in premiums. So $21,000 more in insurance premiums. That's the difference between the y-coordinates of these 2 points and the difference between the x-coordinates of these 2 points. They were separated by 7, and that was the 7 more employees that we were talking about. And where we get the slope of this linear relationship from is we get it from the ratio of this y difference, the $21,000 more, divided by the x difference, the 7 more employees. And so we can kind of say that the slope, 3, that slope is something that attaches not to this pair of points, but it attaches to the entire line, because this relationship is consistent. Every pair of points that we look at is going to have this property that if I divide the y change divided by the x change, I'm always going to get the number 3, regardless of how much the x change happens to be or how much this y change happens to be. They always stand in the same ratio, 3 to 1. And so the way that we gained meaning out of the slope, if you recall from last week, in other words, if we were to describe this number 3 to shareholders, investors, board members, and so forth, people who are not actively taking a class in mathematics or teaching a class in mathematics, I don't want you to just be able to explain this to me. I want you to be able to explain this to other people in your world. So the way to gain an interpretation of that is, as I've done up here, turn it into a unit fraction first of all. So turn it into 3 divided by 1. Sometimes when your slope is already a fraction, it'll already kind of pop out to you, but when it's just a whole number, put that 1 in the denominator to remind yourself that every slope, because it's a ratio, is a comparison between two kinds of change. In this example, it's a comparison between the changes in health insurance premiums, that's the numerator, the y's are on the top in a slope, remember, the comparison between changes in premiums and changes in the size of my employee staff, right? That's what I get on the bottom. And so how I would interpret this number 3, which now I've turned into the fraction 3 over 1, is starting by contextualizing the numerator. 3, remembering that the units of my y values here are thousands of dollars in premiums. So I'll write here $1,000 in premiums. So that's how I can contextualize the numerator, that 3 that's sitting upstairs. The 1 downstairs, remember, that was a change in my x value. That counts the number of employees. So that's how I'll contextualize the denominator here. This 1, I'll think of that as 1 employee. And now all I need to do is I need to add some framing language that indicates to the reader that there's a relationship between these two quantities, and also that these two quantities don't represent absolute numbers of employees or health insurance premiums, but they represent changes, additive differences, if you like, between two different observations, two different measurements from my data table. So the first thing I want to do is I want to add words like increase or decrease. And since both of these, numerator and denominator, are positive, let me add a little plus in front of them to reinforce that. I'm going to add the words increase of in front of each. So this 3 in the numerator means an increase of $3,000 in health insurance premiums. This 1 in the denominator means an increase of 1 employee, so I hire 1 more person, and that's what that 1 might mean down there in the denominator. Sorry, 8 o'clock in the morning, gotta have some coffee for this. You probably do too, if you're watching this live. So that's what those mean. Now I'm just gonna finish this off by connecting these two clauses with some additional grammar here that indicates that what there is a relationship. And so usually the words that I'll use are things like for each. Actually, for each is probably not what I would use in the first clause here. I might use that in the second clause. You'll see why, I think, in a second. For each. And then maybe here I will say there is. All right, so now I've written this sort of paragraph. Let's read it from beginning to end to understand what it's saying. There is an increase of $3,000 in health insurance premiums for each increase of 1 employee. We could also write this in the other way. For each increase of 1 employee, there is an increase of $3,000 in premiums. But make sure that any time that you're writing down a slope and trying to interpret what a slope means, there always needs to be perspective from both the x variable and the y variable's changes embedded within that slope. If you're not saying something about both x's and y's, if you're not using the units of both x and y, so both employees and thousands of dollars in premiums in this example, then you're probably not giving the full picture of what the slope is trying to tell somebody. So make sure that when you write down a paragraph that contextualizes and interprets a slope, that you're saying something about both of the quantities that are being related in an example like this. And of course, last week we talked about what to do with that slope. It becomes one of the parameters, it becomes the m in the y equals mx plus b formula that describes this linear relationship. So we found m, we plunked it down in here, and then we were done with that. What we didn't talk about too much last week is we didn't talk about the intercept, the y-intercept, the b in the y equals mx plus b template. We didn't talk much about how to find it. We also didn't talk much about what it means. So let's talk, first of all, about what it means, because that, I think, is going to get us to where we want to go today. So if we understood the slope, I think the slope is the harder one to understand sort of what it means and where it comes from, just because of the fact that the slope is a relationship between quantities and is not really a single quantity in and of itself. Right? But the intercept, on the other hand, if I redraw my line through my data points here, the intercept is called an intercept because it's the place, it's the point at which my line intersects the y-axis. And by y-axis, of course, I mean that vertical line which passes through the origin, that one that's right there. That over a little bit. So the intercept is the point, the y-intercept is the point at which my line intersects the y-axis. So on this graph over here, I will find that intercept right down there. So let me add a point right there. This point is what I would call the y-intercept for this line. But of course, points have two coordinates in the Cartesian coordinate system, right? They have an x-coordinate and a y-coordinate. So if I want to describe this intercept, I need to use both an x and a y value. But the first thing we notice is that for all of the points along the y-axis, the one thing that they all have in common is that to get to them, I start at the origin and I don't move to the right, I don't move to the left, I only move up or down. And therefore, because I'm not moving to the left or the right to find those points from the origin, the x-coordinate of the points on the y-axis will be 0. That's a big enough deal and easily enough confused that it's worth writing down up here. So on the points on the y-axis, the x-coordinate is equal to 0. And as you might expect, the opposite is true for points on the x-axis. So this horizontal line through the origin, those would all have y-coordinates equal to 0. This is something that's easy to get turned around in your mind if you're not thinking too slowly about it, if you're trying to rush through and think about the y-axis. Sometimes people hear y-axis, they think y is 0. In fact, it's the other way around. Okay, so then what is this number, this b in y equals mx plus b template, telling me? This number is negative 13. And if I look at this graph over here, negative 13 seems like a reasonable y-coordinate for this point. It's underneath the x-axis, and it's just a little more than one of my little grid lines south of the origin. And my grid lines, I can tell from the graph here, they look like they're counting by tens. So it would seem like if I'm a little bit more than one grid line south of the origin, being a little bit more than 10 south of 0 is where I would find myself. So negative 13 is the y-intercept. And then you might ask, well, what does that actually mean? You should ask, what does that actually mean in the context of this problem that I'm trying to solve, right? What does that mean in the context of numbers of employees, health insurance premiums, all of that wonderful stuff that sort of gave us our phony data table here in the first place? How would I explain the meaning of that number negative 13 to, I don't know, my boss or something like that, who might not be a mathematician? So the key to answering that question is actually found right here. The observation that on the y-axis, x is equal to 0, but x has a meaning, right? When our data is contextual, x is my number of employees. So one way of understanding what this intercept is trying to tell me is by writing down if I had no employees at all, 0 employees. That 0, again, coming from the value of x being 0 on my y-axis. So if I had no employees at all, then this number, negative 13, would be my y. Remember, it's sitting in a y coordinate, right? And that means it's describing something about the y variable in this relationship, the thousands of dollars in premiums. So bringing this number out here, if I had 0 employees, I would pay, and then this is going to sound weird, negative 13 thousands of dollars in premiums. Run out of space there. Okay, so there is a sentence, a complete sentence, that contextualizes the meaning of the y-intercept in this example from last week. If I had 0 employees, so if I cut everybody, including myself, from the company, presumably, then I would pay negative $13,000 in health insurance premiums. That's an honest interpretation of what this intercept means. But what you're probably saying, or I hope you're saying to yourself right now, is it doesn't make a whole lot of sense. And the number one thing that I hope you take away from particularly these last couple of units in our course, the one on algebra that we're talking about now, and also the one about probability and statistics that will close out our course, the one thing I hope everyone will take away is the notion that mathematics should make sense. Right? And if your mathematics comes from a place where you've taken some data or you've collected some information about the world around you, and then the mathematics makes a prediction that doesn't make sense, then there's probably a reason behind that. It could be a number of things. It could be, for one, it could be that the mathematics that you chose to use to model the situation might have limitations, and we're trying to extend beyond those limitations. I think that's the case in this example, right? That the amount we pay in health insurance premiums is probably pretty well predicted by this equation when I have a number of employees. But there's a lot of things, if you look into health insurance law, or a lot of things in the small business tax code and so forth, that small businesses with only 1 or 2 employees tend to be governed by very different kinds of tax structures and health insurance obligations and all these things. Those are very different for very small businesses than they are for very big businesses. That's kind of maybe an economics and politics lesson outside of what we're talking about today in mathematics. But it's to suggest that that might be one of the reasons why the mathematics here is making a valid mathematical prediction that doesn't appear to be a very valid practical prediction. Because there's things probably that qualitatively change about the relationship between employees and thousands of dollars in health insurance premiums as the number of employees gets very small. It's probably also true if the number of employees were to get very big. If I were to suddenly find myself at Amazon.com with hundreds of thousands of employees, probably this same relationship between employees and premiums is not the case for a place as large as Amazon either. So one of the things that we come to appreciate from the process we're talking about today is that the models that we fit to data, the equations that we discover out of data, generally are only as good as the data that surround them. And if we try to take them too far through a process of what we call extrapolation, so what I tried to do is extrapolate this down from 12 employees down to 0. If we try to take it too far out of where the data arose, then the possibility that that model becomes less and less well predictive of reality increases. So the more that we try to push models away from their data, the more likely that we're going to be led astray by the mathematics, which is sound, but the model no longer becomes as sound further away. And if you're interested in the details behind that, taking a class in elementary statistics or even intermediate level statistics, if you're taking a social science major, for example, you might talk about things like analysis of variance and regression fitting and that kind of stuff. That's kind of where you dig more into the mathematical and statistical details of why that happens. And when it does happen, how badly can it happen? Because after all, a lot about uncertainty, as we'll talk about in the last part of our course, deals with, okay, I know that there's going to be a mistake here. I know there's going to be some error. How big can that error be, and how can I plan around that kind of error? But for us today, that takes us too far afield. We just care today about how to discover and interpret these two parameters, the slope and the y-intercept of a linear relationship, and to be able to describe to people who are not taking a math class at the moment what those things actually mean. So let's take our next step forward then, and let's try and come up with a set of real-world data that we can just hit it with a discover a linear relationship between that set of data, the quantities measured in that data, in a way using technology that will tell us a slope and an intercept for the predictive relationship between those two quantities. And then we'll be able to do the same process with those as well. So I need to get a couple things up ready on my computer screen. While I'm doing that, if you're watching today and you have questions or things you want me especially to focus on over the next half an hour, please drop those either into the Twitch chat and they'll show up in the video, or drop them into Slack and I'll get your Slack message as well. So just give me a couple minutes to get my materials here set up for the next exercise that we're about to do. Another 1 minute or so. If you're watching this after the fact, you can skip ahead in the video without fear of missing anything. Okay, so let me wipe the slate clean here so that we have room to think for the remainder of our time together. So we talked about the slope, the interpretations of slopes and intercepts, right? What do they mean once we know what they are? How do we describe them to somebody who might not be taking an algebra class at the moment? And then the second place that we need to go is how do we discover a formula? In other words, you might think of how do we discover a slope and an intercept out of a set of real-world measured quantity data. So here's what we'll do. I've got a data set here that was just actually taken from a statistics textbook. So this may or may not be real life, true to life data. But here's what the data look like. And by the way, before I sketch this out, I want to continue with the framing that we talked about last week, where everything that we talk about, I want to be able to talk about it in these 4 different modes of mathematical communication. I want to be able to use words, a verbal description. I want to be able to use data, numbers. I want to be able to use graphs or illustrations, visuals. And then I also want to be able to use algebraic formula. And so everything that we talk about, I want us to be able to talk about it in all 4 of those different fashions during our time today. So let me go grab the data set, and then we'll get this plane off the ground here. So the data set relates 2 quantities. And I'm going to call them x and y again, the way that we did last time, just to make sure that the meaning of what we're doing is not obscured by thinking about different variable names, although it's probably a good practice to give variables meaningful names in general. So x here is the score. Let's say it's the percentile. We're not going to talk too much about percentiles until the 3rd part of the course, but we're just going to think of these as numbers. Percentile score on math SAT exam. So we have a group of 5 students, let's say, and I know what percentile they scored on the mathematics SAT exam, and those are going to be my x values. And then the y quantity is going to be the final grade in their statistics course. So they've completed a course in statistics, and so I have this information on all 5 of the students that are going to be a part of my data set. I know how they did on the math SAT exam whenever they took it. I know how they did in their statistics course when they finished out that semester, and I'll be able to correlate, hopefully, those 2 quantities one with another. So my first student scored a 95 on the math SAT and an 85 in their statistics course. My second student had an 85 on the math SAT and got a 95 in their statistics course. Student number 3 had an 80 on the SAT and a 70 in their stats course. Student 4 had a 70 on the SAT and a 65 in their stats course, so they pulled a D. And then the last student got a 60 on their math SAT and pulled a 70, a C minus, in their stats course. All right, so chances are you probably didn't see me writing those down just a second because I've been flipping back and forth between screens. This whole experience of Twitch streaming has convinced me I need a second monitor, I think, in my office, so we'll see if I can make that happen someday. So sorry for the screen flipping, but here's our data set, right? 5 students, and from those 5 students, I know how they did on the math SAT exam, percentile rank that they got on the math SAT. And I also know how they did in their college stats course, what was their final grade as a percentage, right? So here are my C minus students, here's a B, here's a D, here's somebody who got an A, right? So one of the first things that we probably notice is that there's not as obvious of a correlation between these quantities as we might have expected. Naively, if I'm thinking about how these quantities are related one to another, I would probably expect that students who did better on the math SAT exam in high school would have a pretty good chance of doing better in their stats course than students who did not as well on the math SAT. But that doesn't seem to be borne out by the data. So let's take a moment and actually get a graph. I'm going to go back to, for the moment, I'm going to use Desmos because I like how Desmos graphs look better than I like Excel's graphs. But we are going to switch over to using Excel here in just a moment. So don't be too disheartened here. So in Desmos, what I'll do to get my data is just insert a table. And in the X column, I'll just put in my X values, my SAT scores. So they were 95, 85, 80, 70, and 60. And in the Y column, the course grades in statistics, 85, 95, 70, 65, and 70. Notice nothing's happening on my Desmos graph over here. That's only because we are not in the correct window. We're looking only minus 10 to 10. All my numbers are closer to 100. So I'll just scale out my x-axis so that it goes up to, let's say, 110. Same thing, y-axis. I'll scale it so it goes up minus 10 to 110. Just so that we can see enough of my data. And the first thing we notice is, again, the relationship is not as clear-cut as we would have expected. We can't, for example, draw a single straight line that goes through all these data points. I'm going to take this opportunity to just label here SAT percentile. That's my x-axis, and the y-axis is statistics course grade. And so the relationship between these two quantities is not as obvious as we might have wanted it to be. Right? And so if I were to try to draw a straight line through these data points, that straight line that I could draw through these data points is bound to not pass through most of them. Right? In fact, looking at this data, it doesn't look like there are any more than 2 of these points that I could even draw a line through. No 3 of these points lie on a common straight line. So this is the challenge, right? If I want to be able to somehow model this relationship using a linear equation, what I'm going to have to give up is I'm going to have to give up my expectation that this model exactly predicts the values, really, of any point along this line. The best that we can hope is that it models sort of a general overall trend into which real life has added a bunch of noise and variability into. It might also be that maybe a linear function is not the best choice for how to model behavior like this. Maybe a different kind of function model could be more valuable in doing this. Or maybe there's so many other variables that go into this relationship that we're trying to be too simplistic in modeling it as just a one-to-one relationship, right? If I only know math SAT score, I'm going to be limited in how much ability I have in predicting a student's college statistics course grade. That's probably the most likely explanation, that there are other variables that are what we call mediating this relationship. Just knowing math SAT score is not by itself enough to be able to predict a student's statistics course grade. So with that caveat, though, what can we still say about this relationship? Right? Can we still model this with a linear function? And if so, where is that linear function going to come from? So I said we were going to use Excel for this, and we will. But I also want to show off a neat feature of Desmos. Because Desmos, your online graphing calculator, can also do linear regression. And this can be a really handy way of sort of coming up with a quick and dirty linear regression. So how to do it with Desmos is write down the equation template that you're trying to fit to this data. For us, because we're using a linear equation, I'm just going to add in a note here just to write down. We want a linear regression. So type in a linear equation template. And when I say template, what I mean is that thing that's been drilled into your heads by every algebra teacher you had up to and including myself, y equals mx plus b. Okay. So this is how I like to start my linear regression in Desmos. Just type it in, y equals mx plus b. But we need to now tell Desmos that what we want to do is we want to fit this equation to this data. And in any data table in Desmos, it uses these subscripts, x sub 1, y sub 1, to represent the data that are in that table. So the first thing I want to do is change the x and the y in this template into x1 and y1. And immediately Desmos kind of freaks out, because now I'm trying to talk about the same thing in two different places. So the third thing that I need to do is turn this equal sign into a tilde sign. This is the thing that you'll find when you hit Shift and you hit the backtick key. It's probably next to your escape key on your keyboard. If I turn that into a twiddle instead, now Desmos actually does fit a straight line to my data. Again, this straight line doesn't do a very good job of hitting really any of my data points, but it does somehow capture an overall trend in this data in a way that we should be able to talk about. It gives me some statistical data about this relationship down here that I want to take a moment to talk about also. But again, remember that the caveat in any linear regression is that your regression line, this line of so-called best fit, it may be the best fit for all 5 of these data points taken together, but it might not necessarily even pass through one of them, as this one doesn't. Right? This red line doesn't pass through any of my green data points. And yet, it fits all 5 of these data points better than any other line that I could draw on this graph. And so it is what we got. You got to dance with the partner that you brought to the dance, right? And so what we're going to try to do now is get some information out of this red line, right? So what can we say? First thing that we notice is that Desmos has told us values for m and for b, right? It's told me that m is approximately 0.643836, and that b is 26.7808. Let me take a quick moment here and just export a copy of this graph. Just so that we can have it on our whiteboard here in a minute. Okay. I'm just going to jump over, drop it over onto my iPad, and then we'll be able to have this for our continuing discussion here in a minute. Right, okay. All right, so you can't, well, let me switch over for a second. So I'm just going to take that graph that we just generated in Desmos, and I'm just going to drop it here into our whiteboard. There we go. Okay. So this is the picture. This is what we have right now, is we have these green data points that came from my numerical relationship, and then this red line is what in mathematics and statistics we call the line of best fit. It doesn't pass through even any one of these data points, but it best captures the trend, the relationship that all 5 of these data points together are suggesting. So that's what's happening there. And then Desmos here, and Excel will do this in a minute also, has given us values for the parameters m and b, the slope and the intercept. And that was supposed to be our hook into understanding what this relationship is actually trying to tell us. So let's get those, I'm going to get those written down onto the whiteboard here behind my computer screen while you're looking. So the slope here, m, is 0.643836. I'm going to take the liberty of just rounding that off. I'm going to take everything here to 3 significant figures, so let's say 0.644. 0.644. So that's the value of m. And then b, which as we discussed at the beginning of this session today, that's the y-intercept. That's 26.7808. So I'm going to take that also to 3 significant figures, just call it 26.8. So 26.8. And so if we know m and we know b, then we know that y equals mx plus b gives me a template for an equation that describes this relationship. So this equation, y equals 0.644x plus 26.8, that tells us then, what's happening here? Oh, that's what's happening. That is then going to tell me, sorry, my chat window's getting in the way. That then tells us an equation for this red line. So that's what this equation is actually modeling. This is actually modeling that line of best fit. So while we can, let's get some interpretation out of the slope and out of the intercept. Remember, first of all, well, let's start with the intercept first. The intercept is the place where this line intersects the y-axis. And my y-axis is, again, this vertical line that passes through the origin. And so this line intersects the y-axis right there at that point. And so the coordinates of this point are going to be x-coordinate of 0, because y-intercepts always have a 0 for their x-coordinate, because x is equal to 0 on the y-axis. And the y-coordinate is given by this value, 26.8, which again seems like it makes sense. It's in between 20 and 40 here on the y-axis, in a place where 26.8 seems reasonable. So 26.8 is the intercept. Let's contextualize that. Let's say what this quantity means with words. Remember that to contextualize an intercept, it makes sense to always make reference to the x-coordinate as the first part. And the x-coordinate in my example here is the percentile score on the Math SAT exam. So we would say a student who scored 0th percentile, which by the way is impossible. I suppose if you never take the SAT, you're by definition in the 0th percentile on SAT Math, is correlated here to 26.8 in the y-coordinate, final grade in statistics course. So we would say here, earns a 26.8 in the stats course. And I'm just going to recopy that sentence up here in the upper left pane here. So the verbal description here is that students at the 0th percentile of SAT are predicted to finish your stats course with a course grade of 26.8. Clearly that's not a passing grade if we're going by the traditional percentages, points and percentages model of grading, which we don't in my course, as you know. But yeah, so that's what the intercept of this relationship would then be telling us. Let's also contextualize the slope, this number 0.644. What in the world is that telling me? Well, remember, to contextualize the slope, the best advice that I always have is first, write it as a fraction. And by write it as a fraction, I don't necessarily mean try to find a ratio of 2 whole numbers that give me 0.644, but I could just as easily just write 0.644 over 1 as a fraction. The point of it, after all, is to be able to contextualize each of these two things as a change in one of the quantities that's being related by this linear model. Remembering that in any slope, it's always the y quantities on the top in the numerator of my slope and x quantities in the denominator. Y changes on top, x changes on the bottom. After all, remember that the formula to compute a slope out of a set of data is y2 minus y1, the difference in the y values on top, the rise, And x2 minus x1, the difference in the x values, the run, are on the bottom in the denominator of that fraction. So now all I have to do is remind myself that the y changes are stats course grades, the x changes are changes in percentile scores on Math SAT, and I'll just kind of make a note to myself here. This is SATs, this is stats grades, and now I can write a sentence that tells me what that slope actually means in context. So let's get that down on the screen as well. So I'm going to write down, I'm going to actually start this time with the changes in the x value, just for fun, just to make it a little bit different reading than the last one that we did. So 1 percentile on the SAT. Exam. And then 0.644 point, I guess, in stats course grade. And now I just have to add in the language that indicates that these are changes and not absolute quantities. So I want to add words like increase of or decrease of. So I'll add those in here. Since both of these were positive, I will use increase. Increase of. Maybe I'll also, just to switch things up, let me use the word additional. Those are all synonymous, one with another. And then I'll just add in the final words here that indicate that there's this relationship. For each additional 1 percentile earned on the SAT exam, there is an increase of 0.644 points in the stats grade. Since this model actually came out of a set of real-world data that doesn't actually fit this data exactly, let's decorate this with a slightly more expensive word. And by expensive, I mean loaded with sort of jargon and terminology, but we're being super accurate in using this word. Let's use the word correlated. Each additional 1 percentile on the SAT exam is correlated with or correlated to a 0.644 point increase in the student's grade in their stats class. And I'm using the word correlated here very deliberately because the last thing that I want to talk about in today's session is a quantity that tells us just how well a linear model fits a set of data. So this is something that the Desmos window actually told us also that I didn't dwell on, but I want to look back at it for a minute here. So here inside of my Desmos window, there are these statistics up here at the top called R squared and R. These are called coefficients of correlation or coefficients of variation. Those are the fancy statistical names for them. We can think of them as the numbers which tell me how well does this line fit my data. They tell that story in a couple of different ways. I think for our purposes, let's focus in on the value of R for the moment. This is called the coefficient of determination. R is 0.6931. Actually, do I want to do R? Now let's do R squared. Let's talk about R squared, 0.4803. So what in the world does that mean? I'm going to write it down over here. R squared is 0.4803. I'm going to put that down in my numbers section up here, right? Because that's a number that's supposed to be telling me a story. It's a number that's called a statistic because it was arrived at through a process of considering the entirety of the data. Right? All 5 of these data points went into making this number R squared. This is the coefficient of correlation. And statistically speaking, what a correlation coefficient tells me is what percentage of the variability in one of my variables is attributable, is associated to the variability, the associated variability in the other change. So under this model, under this linear y equals mx plus b model, there's a relationship between x values, SAT scores, and y values, statistics course grades, right? There's a relationship between the two. And so when one of them has variability, uncertainty, variation in it, that will cause variation in the other one. And the correlation coefficient tells me how much of the variability in one of these occurs as a result of the variability in the other one, right, in this model. And so we can kind of think of this number as a percentage. This will always be between 0, which would be 0%, and 1, which would be 100%. So these correlation coefficients exist on a spectrum. From 0 to 100, r squared equals 1. And again, if we think of this as a percentage, 100%, right? And at the other end of the spectrum, r squared equals 0. And that would be 0% if we're thinking about these as percentages. Right? And at a level of 100% for a correlation coefficient, that would mean that all of the variability in one of these quantities arises as a result of the variability in the other quantity. And what that would mean is that there's no other quantities out there that mediate that relationship between the variability in the x's and the variability in the y's. And so in that situation, we have a perfect match between x's and y's in this model. So if we were to get a correlation coefficient equal to 1, that would mean that we have not just the best fit, but we have a perfect fit. That my line would actually pass exactly through all of my data points when I have r squared equal to 1 in that case. On the other end of the spectrum, when r squared is equal to 0, it means that none of the variability that exists in one of these quantities is attributable directly to the variability in the other. And so what that would mean is that as one of these quantities changes and varies and fluctuates, the other one does not do anything in response to that under this linear model. And so that would mean that these two quantities are virtually uncorrelated. In this situation, no line that I can draw through my xy plane would be better than any other line that I could draw in modeling the data. And so that's kind of a nightmare scenario. That means that we've not predicted any of the relationship between the variability in these quantities using my linear model. Of course, from real-world data, most data sets lie somewhere in between, like ours, for example, 0.4803. We could think of that as 48.03% if we like. We're going to talk more about percents later on this week, so this is kind of good practice. 48.03%. And so that situates this model somewhere in the middle, maybe right about here or something, right? 0.4803. And so it's at a place where this is definitely not a perfect fit. We knew that from the graph. But it's also not completely uncorrelated. There's at least some amount of the variation in students' stats course grades that is attributable to a difference in their math SAT exam. It's correlated to a fluctuation in their math SAT exam scores. And so I would probably say this is not a very strong model. What constitutes a strong model varies from person to person, but often statistically, if you're doing a two-variable regression like we are here, people like to see things that are at least 90% and higher before they are convinced that this is a pretty good model that's useful for its predictive power. But it's not completely uncorrelated either, right? There's a weak, let's say a weak correlation. There's a correlation, but it's not a very strong correlation between quantities in this model. There's a chance that maybe if we gathered more data, if we had 50 or 500 or 5,000 data points instead of just 5, that maybe a clearer picture would emerge, or maybe it wouldn't. Maybe all those other mediating factors that aren't in the model would continue to confound this simplistic analysis. But at least we would have a little bit more certainty in that case that there's more than meets the eye to this relationship. So that's what these correlation coefficients tell me, right? It tells me how well does this line of best fit actually constitute a line of good fit, right? This is the best that we can do with any line, but how good does it actually do? How closely does it actually hew to the data itself? And in this example, where 48% of the variance in y is correlated with variance in x, that's not a particularly high correlation, but it's not nothing either. So I want to end by making good on the promise I made earlier in the video, which was to be able to do this with Excel and not just using Desmos. Desmos is great. I mean, we just did in a couple of clicks in Desmos what we wanted to do here. But for staying power, for your future careers and so forth, graphing calculators and Desmos and those kinds of tools are probably not what you're going to be using in practical applications. So let's pull out Excel. So all I did here was I opened up a blank Excel worksheet. I'm going to zoom in on a little bit so it's a little easier to read in the video. And let's look at the process. So Excel is a spreadsheet software, and what that means is that it just gives you a bunch of blank cells in which to place observations, data, numbers. You can also put text and stuff. So first thing I'm going to do is recreate my data, my x's and my y's. So the x's here are my SAT percentiles, so I'm just going to write that up here to remind myself. And my y values are my stats course grades. All right, so let me just put in my data. My x's were 95, 85, 80, 70, and 60. And all I'm doing here is just typing these numbers into these cells and hitting an enter key. 85, 95, 70, 65, 70. So all I've done is I've dropped my data table into a blank spreadsheet in Excel. And if that's all you can do with Excel, that's not nothing. That's pretty good. We're already probably to week 3 or 4 of a good course in how to use Microsoft Excel. What, of course, I want to do now is do the same thing Desmos did. Come up with that graph and that line of best fit. So now is when things get a little more specialized. Step 1 for Excel is to create the graph, what we call a scatter plot. So to do that, I'm just going to highlight all the data in my data table. I'm going to include my X and Y, my little column headers, in addition to all of my observations. Highlight all of it. And then, depending on whether you're using a PC or a Mac, you'll notice I'm using a Mac in this video. This next step, I think, is the same if you do it the way I'm about to do it. Right-click your mouse. And it should come up with a menu of things that you can insert. If I click Insert, oh, sorry, not that insert. I've already botched this. Rather, I want the Insert ribbon up here at the top. And that exists on both the PC and the Mac versions also. So head up to the Insert ribbon with your mouse. And then choose to insert a chart. In this example, I want a scatter plot called an XY plot. So I'm going to choose the scatter plot menu here. And I'm going to choose the version of a scatter plot that only just plots the points. I'm not interested in Excel trying to connect these dots. I just want to show me the dots. And once I've done that, we get the graph that looks an awful lot like the graph that Desmos made for us. So now how about that line of best fit? To get that line of best fit, what we want to do in Excel is, again, right-click your mouse on one of the data points. And when you right-click the mouse on one of the data points, one of the options that pops up is called Add a Trend Line. Trend line is Microsoft Excel speak for a regression. It's called a trend line, I think, because that's what people in the world of business, where Excel is kind of used the most, tend to think of these things as. So I'm just going to click to add a trend line. And Excel is going to give me some options for that trend line. Let me scoot this over a little bit so you can see all of them. First of all, it's giving me some options of different kinds of functions to fit to this data. Right now we're talking about linear functions, so I'm going to keep this clicked at linear. But if you wanted to use a different kind of model, you could do so. We also want Excel to show me the equation and the R-squared values for these. So I need to tell it those things explicitly. These might appear in a different spot if you're on PC compared to Mac, but they will always be there somewhere. Display equation on chart and display R-squared value on chart. Make sure those two things are checked. That way you have everything. You have the graphical picture and you also have the formula picture to fill in for this regression. And so here it is for this example. Same equation that Desmos came up with for us, as well as the same correlation coefficient R squared, 0.4803. One of the things that Excel does differently than Desmos is it only draws the regression line as far out as the data itself. So it doesn't draw it all the way back to the x-axis and y-axis the way that Desmos did. And that's, again, kind of a cautionary thing on the part of Excel. Because, again, the further away that we get from the data, the less that we should be able to trust the predictions that that regression model makes. But here again, Excel is giving us the same information as we got out of Desmos. If we were going to use this graph for something professionally, you would also want to give it labels. So statistics grades and their correlation to SAT scores. Give the chart a title. You probably want to give the axes. You want to give the axes some titles, so I'll add an axis title. Math SAT percentile. And do the same thing on the y-axis. This would be statistics course grade. Whoops. Just because I want this graph to have meaning to anybody who's looking at it without me having to explain where this comes from. But again, this is how Excel does that same process, right? Just to review what we did, we just typed the data into a blank Excel spreadsheet in columns. You could do this in rows as well if you wanted to, the way that I showed it on the whiteboard a minute ago. But then highlight the data, including the column headers, insert an XY scatter chart, and then right-click on one of the data points in that scatter chart to choose to add a trend line. Make sure you tell it to include the formula and the correlation coefficient when you add that trend line, and you'll have everything that we also got out of our Desmos online graphing calculator. So the most important thing about today, to take away from today's session, is how to contextualize, how to talk to somebody who's not a math student or a math teacher about what a slope and an intercept actually mean, why they should care about them. I'm not going to get anywhere by just holding out the number 0.644 to somebody. I need to be able to say, this means that a student going up by 1 percentile on the SAT means that we expect their stats grade to be correlated to 0.644 points higher, right, according to this linear model. To be able to do those explanations, that's why we think mathematically and why we practice mathematics. One of the reasons why we think and practice mathematics is because it has this value, this currency, this precise ability to communicate a concrete thought about a quantitative situation like this one to the world around us. So I hope this helps with finishing up the assignments from week 5 of the course on the applications of linear functions. We're going to turn the page later this week in a streaming session and talk about other kinds of function models as well. So we're going to be looking at exponentials later on this week. So I'm going to have our streaming session a little bit earlier than usual just to help us get a little bit ahead of it. And I look forward to seeing you again later on this week.